Hi everyone. Welcome back to Dave's Math channel. I'm your host David Tear, and this is my 8th video on my sub-series on integration of my series on first year calculus. And today I'm going to talk about another very powerful integration technique known as integration by parts. And you can see what it looks like on this slide. I'm going to explain this. So anyway, let's begin. So there's two ways you can write the rule for integration by parts. You can write it in as equation 1, which is the same equation I showed you on the introductory slide. Just says the integral of u dv is uv minus integral of v du. I have to explain this a little bit. U and v here are just arbitrary quantities that depend on some other variable, which we might as well call x. And if that's the case, then you get this rule. But now, rule 2 is sort of a special case of that. Say u is just a function of x, which we can call f of x, and v is just another function of x, which we can call g of x. So in that case, u is equal to f of x, and v is equal to g prime, dv is g prime x dx. So your first integral just looks like this, the integral of f of x times g prime of x dx. And then uv is just f of x times g of x, and now you're subtracting the integral of v du, which is the integral of g of x times f prime of x dx. So you see the 2 follows easily from 1. But anyway, how do we prove this? We really only have to prove rule 1, since I already showed you how rule 2 follows from rule 1. So how do we prove this? Well, it's actually pretty easy. We start with the product rule for derivatives, or Leibniz rule, if you like. So if u and v are just two arbitrary quantities that both depend on a variable x, and they're both differentiable with respect to x, then we just have d dx of uv. This is just the product rule I'm writing down here, which you may remember is equal to u dv dx plus v du dx. That's nothing new. You've seen this already. Now, the next thing you want to do is multiply everything by dx. And if you do that, you get differential quantities on both sides. You get d of uv equals u dv plus v du. I think I talked briefly about differential quantities a few videos ago. Just think of this as a small change. So really what this equation is saying here is if you have two quantities, u and v, if you make a small change in their product, d of uv, that's all that means. It's equivalent to making multiplying u times a small change in v plus v times a small change in u. That's all this is saying. And now we just do a little bit of algebraic manipulation here. The next thing we do is we subtract v du from both sides. If you do that, you get d of uv minus v du equals u dv. Now there's just a couple more steps. First, you switch sides, so you're going to get u dv equals d of uv minus v du, and now you integrate both sides. And if you do that, you will get equation 1. Get the integral of u dv, and if you like, the integral of duv is just uv, and then you're subtracting the integral of v du. Voila. And I already explained how you can get equation 2 from equation 1. So that's the proof of integration by parts. And like I said, it's a very powerful technique, and I'm going to show you several examples. So, and these are all very common examples. You'll see these a lot. So anyway, let's first integrate the natural logarithm using integration by parts. Now, what we're going to do here, and this example is a little bit unusual, because usually when you use integration by parts, you have a product in your integrand. Here you don't. I mean, you can think of one of the terms as just being 1, if you like. Yeah, dv is just dx, if you like, and u is ln x. We don't have much else of a choice here. So if u is ln x, then du is equal to 1 over x dx, because the derivative of ln x is just 1 over x. And if dv equals dx, then v is just x plus some integration constant c, but we usually set c equal to 0 when we do this, so we just have v equals x. So if you do that, you notice that the integral we started with does have the form u dv. Here u is ln x and dv is dx. So now we can apply integration by parts. So we just write down the rule for integration by parts. You should always do that to start. So I is equal to uv minus integral of v to u. And now u is ln x, and we're multiplying that by v, which is x. And now we're subtracting the integral of v, which is x, times du, which is dx over x. Now we can just do a little bit of simplification. So we can write the first product as x ln x, and we can notice that the x's and the integral cancel, and we're just left with the integral dx. So, and the integral dx is easy. That's just x plus c. So we get x ln x minus, because you're subtracting the integral, you get x ln x minus x plus some integration constant c. And the last thing you can do, if you want, you can group terms, because notice that the first two terms are both divisible by x, so we can factor out x. If you do that, you get x times ln x minus 1 plus c. So that's how you do that one. And let's do a few more examples. So this is one you'll see a lot. How about the integral of x times e to the x dx? Well, this is one where it's pretty clear that you might want to use integration by parts. And in general, here's a general rule. When you have a product, you can divide it into two things, and you want to let u be something that's easy to differentiate, and v be something that's easy to integrate. Well, e to the x is very easy to integrate, right? The integral of e to the x is just e to the x. So you really want to let v equal e to the x here. And then u is x. So if u is x and v is e to the x, then you get du equals dx and dv equals e to the x dx. And now you'll notice that the integral does have this form, integral of u dv. And now, once again, we apply integration by parts, so we know that it's equal to uv minus the integral of v to u. We plug in everything again. U is x and v is e to the x. So our first product is x e to the x. And now we're subtracting the integral of v, which is e to the x, times du, which is dx. So that's just the integral of e to the x dx. That's an easy integral. That's just e to the x plus c. So we're going to get x e to the x minus e to the x plus c. And again, we can group terms. We can factor out e to the x. And the first two terms, we just get x minus 1 times e to the x plus c. Anyway, so let's do a couple more examples, kind of like that one. How about the integral of x cosine x dx? Well, same idea. And you probably don't want to make v dv equal x dx, because that makes it more complicated. I mean, you know how to integrate that. You're going to get 1/2 x squared, but why make the powers go up? So you might as well let dv equal cosine x dx. That's easy to integrate. V is just sine x. So if v is sine x, u is x. So then du equals dx, and dv is cosine x dx. So now we have the right form. Integral of u dv is integral of x cosine x dx. And now we apply integration by parts. So we get I equals uv minus integral of v du. uv in this case is x sine x. And the integral is going to be the integral of sine x dx. Well, integral of sine x is easy. That's just minus cosine x, but we're subtracting it. So we get x sine x plus cosine x plus c. So that's how you do that one. And a very similar one I'm going to finish with. How about the integral x sine x dx? Same idea, really. So now, again, we're going to let u equal x. This time we're going to let v equal minus cosine x, because the derivative of minus cosine x gives you sine x, which is dv. So dv is sine x dx. That means v is minus cosine x. So again, we use integration by parts. Notice that the integral has the right form, integral of u dv, and that's equal to uv minus integral of v to u. U in this case is x, and dv is minus cosine x. So we're going to get minus x, or v is minus cosine x, so we get minus x cosine x plus the integral of, we're subtracting the integral v to u. That's going to, since v is minus cosine x, we get a plus in front. So we get plus the integral cosine x. And integral cosine x is easy. That's just sine x. So we're left with minus x cosine x plus sine x plus c. So that's how you do integration by parts. Like I said, very powerful technique. And it's usually pretty clear when you want to use it. So it's a very useful rule. Anyway, that concludes my talk for today on integration by parts. Thank you for watching. Long live math, and I'll see you guys next time. Bye.